All right, so we'll start with this part two of this week three module. We are discussing about durability aspects in reinforced concrete design. This would be the lecture 3.2. And in this lecture, we are going to focus on different deterioration mechanisms. We will start with chemical actions. Okay, and that would be the focus of this part of this lecture. And the learning outcomes are the student should be able to explain the different concrete deterioration mechanisms that are available and what are the different chemical attacks are there in the concrete and what are the effects and how we can prevent these or minimize the effect of these attacks. We are going to discuss. Right. So, the last lecture we discussed what are the the what is durability, why is it important that we need to properly consider that in the design. Now let's see what are the different deterioration mechanisms of concrete are available. The overall deterioration mechanism can be classified them as concrete deterioration and a reinforcement deterioration. Reinforcement deterioration is basically corrosion. We have two types of corrosion. We will talk about that. With respect to concrete, we can classify them as mechanical, and mechanical actions like abrasion and erosion can relate it to concrete deterioration, or it could be due to physical actions like freeze and thaw, which is a significant effect, especially when your concrete is under sub-zero temperatures. Then concrete also can undergo chemical attack, which is what we are going to discuss in this part. We are going to talk about there are two major aspects or chemical attack that is going to lead to concrete deterioration. One is the alkali aggregate reaction, another one is the sulfate attack. Right. So corrosion happens in steel. Either it could be due to carbonation-induced corrosion or it could be chloride-induced corrosion. Mostly the chloride-induced corrosion is a very significant aspect. However, carbonation is also can reduce the pH and then lead to other deterioration mechanisms. So they're all interrelated when it comes to the the performance aspect of concrete as a system. In this part of the module, we are going to focus only on the chemical deteriorations or chemical attack. Uh, we will first start with alkali aggregate reaction and then we will discuss about sulfate attack. Okay. So now what is alkali-silica reaction? Is called as ASR. Sometimes it is also called as alkali aggregate reaction, AAR. Both are same. So what is it? It is a chemical reaction that develops between reactive silica that is present in the aggregate and the alkalis that are present in the cement paste, which is called as alkali-silica reaction. Now, why is that we should be concerned about? The reason is it is going to the reaction product between the reactive silica and the alkalis is going to create cracking in smaller structures, or it can lead to expansion and severe cracking in large structures like dams. Okay. Now, as we've seen in cement, we always have a lot of alkalis like sodium oxides and potassium oxides. So alkalis are always available either from the cement as an internal source, or it can be coming from the external environment as well. Now, silica is hugely present in the aggregates. It comes from aggregate. Now, what happens? Both of them, when they react, it forms a gel, and then this gel will start absorbing water, and then it will swell. Okay. Now, because of the swelling, what happens is it is going to produce a lot of stresses in the surrounding areas, and it is going to create a lot of cracking and spalling. Now, the thing is, this gel can form if it is not going to swell if the water is not available in the concrete. So, this is one way that if you are able to control the availability of moisture in the concrete system, again, the gel cannot expand and it cannot create more cracking and spalling. So, this is one way of controlling, in fact, the effect of alkali-silica reaction. Right. Now let's get into this. This is a small illustration that explains what happens in alkali-silica reactions. So as we've seen in the cement paste pore solution, we have a lot of these alkalis, sodium, potassium, calcium, hydroxyl ions, right? And now let's say if you have also have reactive aggregate, the aggregate that has silica, that is reactive silica, then what happens is these uh, aggregates with the reactive silica will start reacting with these alkalis that are available in the cement pore solution. So what will happen is all of them will start reacting, and it forms this like what we have seen, this kind of a gel, okay, which is called as the alkali-silica reaction gel. It will form around the aggregate, and also if aggregates are porous themselves, then it can also form within that aggregate. Now this gel will start absorbing, as we can see, if you start absorbing the moisture from the surrounding concrete, and then the gel will start expanding. So you can see that the gel has expanded now. Now when the gel expands, it is going to create a lot of pressure around the surrounding areas, and then the pressure can also exceed the tensile strength of the concrete, and it can create a lot of crack. So this is the mechanism through a very simple illustration. Right. Now, what are the factors and causes for alkali-silica reaction? As we can see, alkalis are present in the cement. Sometimes alkalis can enter from external environment as well. Then when you have a reactive silica in the aggregate and then moisture, all of them combined together, you will have alkali-silica reaction. Why is it critical? Because it's going to form expansive gel that is going to create pressure, and it is going to create a lot of crack. So that's what important. Again, the causes of ASR, it's also the various factors that will affect this ASR. The concrete age, depending upon, in fact, this ASR also happens over a long period of time. Sometimes the humidity and temperature also can play a major role, how fast this ASR can play a role. And higher alkali cement, if you're using, of course, that is going to aggravate your alkali silica reaction. Similarly, moisture content. As we said, if you want to contain the DSR, one way is to prevent this moisture availability close to this reaction ASR gel. Then it will not increase in volume, and it will not create cracking. Now you can see what are the effect of this alkali silica reactions. You can see in the concrete pavement, you have all these kind of alignment cracks that is happening, right? And similarly, you have this random cracking, which also we call that as map cracking. Okay, so this is also because of the alkali silica reaction, and you can see in these dams also you can see this kind of map type of cracking. So these are the effects due to alkali silica reaction. Now, what are the preventive measures of alkali-silica reactions? As we have seen it in the first part of the module also, one way is to use supplementary cementitious material. People have done some experiments, and we can clearly see in this graph that it is shown on the right. We have in the y-axis, we are measuring the expansion, what it is happening, and higher the expansion, higher will be the stresses that will be induced. So we want to limit that expansion. That's what it is given here. This black color curve is your limiting value that is suggested, which is a 0.1 percentage of expansion limit. Uh, and if you see, there are control concrete mixes that were done, and then some mixes, the binders were replaced with 20 percentage, 30 percentage, and 56 percentage of fly ash. And then sometimes the slag also people have tried, and they replace the cement with 35, 50, and 65. Similarly, silica fume also were added, 7.5, 10, and 12.5 percentage of cement as a replacement. So you can see here clearly for the control mix without any of this SEM, the expansion is about 0.27 or so, which is quite high than the allowable limit of 0.1 percentage. The moment you start adding the supplementary cementitious material, either the fly ash, and higher the amount of fly ash, again, the lesser is the expansion. Similarly, higher the amount of slag, again, lesser is the expansion. And then with silica fume also, with higher the amount, you are having lesser is the expansion. So clearly, addition of your supplementary cementitious materials like fly ash or slag or silica helps in reducing this expansion. And another way is to use low alkali cement. And another important aspect is to use low alkali cement so that lesser alkalis are available for reacting with reactive silica of the aggregate. Another thing is to use non-reactive aggregates. So aggregates have to also be tested so that they do not have reactive silica component. Now, let's say that you have already built the structure, and if you want to limit this crack induced by this alkali-silica reactions. One of the intervention is people do this lithium impregnation, that basically it goes and coats within the aggregate and it will not prevent the gel to form. Okay. However, this is a very costly repair procedure. Only it is absolutely required and cost is not a factor. Then people undertake this kind of repair mechanisms, right? Now, how to assess, what are the test methods that are available for assessing the ASR? We have three things. One is we can do this petrographic examination as per ASTM C295. So what we really do is we take these aggregates and then we do microscopical examination to see whether we are having this reactive silica or not. Sometimes we also do this fluorescent test that indicates whether the reactive silica is not or there. Or what we do is we also make specimens either with cement mortar or with concrete prisms, and then we try to measure this expansion of this prism over a period of time. And if this expansion is less than the allowable limit, then we say that the reactive component of this alkali silica reaction is not really a big concern. So these are the test methods that are recommended by ASTM standards. Right. So now we are looking at, so we have briefly talked about alkali aggregate reaction. So we are now discussing concrete deterioration through chemical actions. And first one is alkali aggregate reaction. We briefly discussed. Now we will discuss what is the effect of sulfate attack. Okay. Sulfate attack also can deteriorate the concrete. So we will talk about what happens when you have sulfate attack. Right. So, sulfate attack, as you can see here, it is a chemical breakdown mechanism where sulfate ions attack the components of cement paste. Okay. So the reinforcement is not really affected because of the sulfate, but it is the cement paste that is attacked by the sulfate ions. And what are the compounds that are responsible for this? Usually calcium sulfate, magnesium sulfate, sodium sulfate, and potassium sulfate. Okay. And you know that calcium sulfate, it is internally available within the concrete because we are using gypsum for controlling the setting time. Now, sulfate attack can be either external or internal. Okay, we'll talk about what is the significance of that. Now, we have various elements that are subjected to soil that can be rich in sulfates, or these elements that are subjected to water that may contain sulfates, right? So, this is one of the testing that people have done, PCA, Portland Cement Association, and they have kept these samples. You can see they have used the rating of concrete at 12 years. You can see where they have done. In fact, they have used the sulfate resisting cement. But if you have a high water cement ratio, okay, you can see that complete degradation at the end of 12 years. Okay, the same set of specimens. They are made with the same type by cement. However, they had very low water cement ratio. They were subjected to sulfate environment. You can see that with low water cement ratio, even though sulfates are present, the degradation is very marginal even after 16 years. So one way to control the sulfate attack is basically to reduce the water cement ratio in your cementitious system. Now the thing is, sulfate attack produce this kind of delayed ettringite, or this ettringite is a needle-like structure, which is an expansive product that is going to create again more pressure on the surrounding concrete. It will create this kind of cracks. Okay, so these are the cracks that are induced by the sulfate attack. These are your external factor, and this is your internal. We will talk about the delayed ettringite formation in the coming slides. You can see that if it is exposed to external also, the one way to control that sulfate attack is by using lower water cement ratio. Right. So the external sources of sulfates, as you can see, soil. Most soils contain sulfate in the form of gypsum, 0.01 to 0.05 percentage expressed as sulfate, SO4, and this amount is usually harmless. And even in groundwater, we may have higher concentrations in groundwater, usually due to the presence of magnesium and alkali sulfates. And other sources can be ammonia sulfate is usually present in agricultural soil because we use ammonia as a fertilizer, and effluent from furnaces that use high sulfur fuels and from the chemical industry also can contain sulfuric acid that will again source for external sulfate. Sometimes decay of organic matter in marshes, shallow lakes, mining pits, sewer pipes, it leads to form hydrogen sulfide, which again transforms into sulfuric acid by bacterial action. So these are the some examples of external sources of sulfate that we need to be careful. So this is, you can see some of the bridge columns in North Dakota in very sulfate rich soil. You can see that complete cement has undergone degradation. You are left with only steel rebar in some regions. And it is also very common to find deleterious concentrations of sulfates in natural and industrial water. So these are the external sources of sulfate. Now, what is the mechanism of sulfate attack? And this external sulfate, if you have a permeable concrete, okay, and you can enter, and it can become an internal sulfate, because if the concrete is permeable, it can enter and it can. So, what is one way to control this is use concrete with low water cementation and use supplementary cementitious materials like we have seen in the previous part of the lecture also. Now, another what happens is once the sulfate becomes external, then what happens is it forms, so let's say, sodium sulfate and reacts with calcium hydroxide, and it can produce gypsum and sodium hydroxide and water. Okay. Now, this is again, it is a product. What will happen is it will again can reform and form an ettringite at a later stage. In the hardened stage, if it is the gypsum is available, it can convert itself into ettringite, which is a needle-like product, and it's going to occupy more volume. That is going to create crack. In fact, ettringite formation happens at the initial period. Because the concrete is plastic, the initial formation of ettringite does not really create issues. Only that delayed ettringite formation in the hardened state, it is going to create cracking issues, which we need to avoid. So one way to avoid is basically, again, make sure that less calcium hydroxide content is available at a later stage, and that one way to reduce the amount of calcium hydroxide available is through use SCM, because through SCM, when you are using supplementary cement, they will use this calcium hydroxide for producing additional calcium silicate hydrate gels. So again, usually when you have higher C3A content, this will form a monosulfate at the initial stage, which is a more stable product. Then it can react with the gypsum if it is available, and it can form this ettringite at a later stage. So that is what it will create, volumetric expansion and cracking, that what we have seen in this figure, and this kind of cracking that you will have. Okay, so that we need to reduce. So one way to control this delayed ettringite formation is by reducing the C3A content. That is what we have it in sulfate resisting cement. Sulfate resisting cement will have usually low percentage of C3A. Right. So now this is for this thing, internal attack. So the internal sulfate can affect internally without any other external contributions from outside environment. So what happens is during the mixing process, we try to use sulfate-rich aggregates or excess gypsum. The gypsum, what you're using it for controlling the setting time. If excess gypsum is available, then again that gypsum will convert and it will form monosulfate. Then further, that monosulfate can react with gypsum to produce delayed ettringite formation. So this is what the delayed ettringite formation. Usually it happens when the concrete is exposed to temperature that causes decomposition of ettringite, and then again when moisture is available, it reforms this ettringite. Okay, so initially ettringite will form, but if you have excessive heat, then what will happen is the ettringite will decompose and form this monosulfate, which is a more stable product. But at a later period, when you have moist conditions are available, again it will reform ettringite, and that is a needle-like structure that will create more expansive stresses, and it will create cracking. So this, we need to prevent this delayed ettringite formation. Now, usually for precast concrete or concrete that is cured in autoclave or at elevated temperature or steam curing, because you cannot, the ettringite will decompose and it will form this monosulfate in a more stable product. And later on, when moisture is available, again it will form ettringite. That is called delayed ettringite formation. That is more possible in precast concrete, concrete cured in autoclave or elevated temperatures. So that are more susceptible for this delayed ettringite formation. Right. Now, what is the mechanism of DEF or delayed ettringite formation induced cracking? Now, this expansion in this paste is caused by DEF that originates in the cracks in the paste, and the aggregate cement paste interface. So usually this ITZ portion between the aggregate and cement paste is where these delayed ettringite will form, right? And then later these ettringite also can recrystallize in the cracks from the submicroscopic crystals which are dispersed through the paste. Okay, and this microscopic image also shows that the ettringite lining expansion rims at this interface you can see. And this is your ettringite lining expansion rims, and it is also it can fill the air voids and in the porous areas of the paste. The only problem is it's a high expansive. It creates high expansion about 2.5%, so it is going to create a lot of stresses, tensile stresses around this delayed ettringite formation. It can lead to this kind of map kind of cracks. Okay, this is due to delayed ettringite formation. We need to avoid. So again, we have seen it in the previous slide. The one way to use reduce this thing is to by use sulfate resisting cement and also use less C3A content in your cement. Right. So now let's see what are the factors that influence. So these are some of the studies that were done in the past. You can clearly say that higher the sodium sulfate concentration when it is exposed. This is in the y-axis. What we are plotting is a expansion after 15 months. Okay. So you can see here with increase in concentration, you are seeing that the expansion is also linearly increasing. So higher the exposure of your sulfate, higher will be your expansion. The next one is with magnesium sulfate concentration, and these expansions are measured at different times 12 weeks, 21 weeks, and 32 weeks. Again, you can clearly see here that with higher the concentration of your magnesium sulfate, higher will be your expansion. Of course, at a lower age, it is less. As the time goes on, the expansion also increases. In some cases, it also kind of plateaus, right? So this is the expansion. So higher the exposure of magnesium sulfate concentration, higher will be the expansion. So that is one thing. Then again, temperature also, people have studied what is the effect of temperature with respect to age. Okay, you can see you are plotting a temperature in the x-axis, again expansion in the y-axis. So you can see at particular temperature as expected. When you give more time, again you are having more expansion for a particular temperature. Again, if you look at for a particular age, for example, let's say at 6 weeks, when you're saying higher the temperature, higher is the expansion, right? Similarly, this is for sodium sulfate and this is for magnesium sulfate. More or less, nearly the expansion is able to increase with increase in temperature, and expansion is also increase with increase in age. So that is what the previous people have found out through their experiments. Now, age of concrete. Again, you can say for a concrete that is exposed to magnesium sulfate, you can see with respect to time, because there is a lot of cracking and degradation that is happening, you can see that at initial time, let's say you have 100% of your strength, and you can see as the time goes on, right, your strength is degrading, because strength is degrading. Why? Because the cement paste is coming out, right? So you also have this kind of mass loss that is happening. So that is also leading to degradation mechanism both in strength as well as there is a loss of mass. Okay, so this is with respect to that. Now, what is the effect of supplementary cementitious material, like what we have seen in the previous chemical attack also? Here people have done some experiments and they are plotting what is the strength with respect to time, okay, in the x-axis, and we have different scenarios that we are considering. One is the concrete made with Portland cement, another one is with sulfate resisting cement, another one with slag, and another one with silica fume, another one with fly ash. So you can see this component, and with the slag I am replacing in fact only 30% is Portland cement and 70% of GGBS, and in another fly ash only 20% of fly ash is added. In silica film 8% is added. So in all of them we can clearly see here that for the Portland cement, which is in the dark circle, and you can see here this is the way it is going, right? As the time is going, the strength is it is reaching almost at about 500 days, it is reaching as low as about 55% of strength, original strength. However, if you start adding supplementary cementitious material, you can see that even at let's say 550 days, if you look at it here, your strength reduction is only about 90 percentage for this fly ash and silica film, fly ash and GGBS addition. Okay, so you can see that by adding, in fact, silica fume, if you see here, it is the reduction is not much only from sulfate point of view, but you have to also see that silica fume also is going to densify your microstructure, and it is going to make the concrete more impermeable. So in that way, you are looking only the chemical sulfate effect here, but it will not let the sulfate from external source to enter as well. So in that way, it is going to be beneficial. So in summary, adding supplementary cementitious materials is going to really help in preventing this strength degradation due to sulfate attack. And so, how do we? What are the other preventive measures? Of course, we have to check the sulfate content in the soil or groundwater where you are constructing, and choose appropriate cement, and use the concrete with low permeability. Again, you can clearly see here that if you are having lower water cement ratio, that is plotted in the x-axis, and you can see that the expansion for different types of cements is again coming down. So one way to reduce the sulfate attack is to use low water cement ratio, and also to use sulfate resisting cement. And we have India also, we have sulfate resisting cement that is available. In the US, they call it as type 5 cement, and also type 2 is also having less than 7% of your C3A. Okay, so these are sulfate resisting cement. It gives. Now, what is the effect on serviceability properties due to this reaction that we talked about? Let's say the alkali aggregate reaction. So, of course, it is going to create crack formation, and then it can lead to more deflection. So, it is going to affect serviceability. Next, the sulfate attack. It is going to increase the stress levels which are resulting from loss of section, because now you can see the concrete has completely come out. In alkali aggregate reactions, you see you have this map type of cracking, but concrete has not completely come out. But here you can see that due to sulfate attack, there is a loss of section also that is going to increase your stress levels. Right. So in this part of the module, briefly we talked about alkali-silica reaction and sulfate attack, and we also discussed what are the mechanism of this chemical deterioration due to alkali-silica reaction and sulfate attack. And the major preventive measures is to use supplementary cementitious material, and also use non-alkali cement and lithium impregnation if you have already constructed, which is having the aggregates which have reactive silica, and also you have a lot of alkalis present in the system. Then to reduce this alkali-silica reaction, one repair strategy is to use lithium impregnation. So we discussed about that. With respect to sulfate attack, again, we can use supplementary cementitious material, or use sulfate resisting cement, or make sure that the place where you are doing construction is not rich in sulfate. Or for example, the foundation, when you are doing it, we need to go for some kind of methods of removing the sulfate, but most of the time it will not be possible. We resort to using sulfate resisting cement or other means to tackle the sulfate attack. Right. So these are the references for this part of the uh, module that we talked about, which is alkali-silica reaction and sulfate attack. And thank you. So in the next part of the module, we will talk about other deterioration mechanisms. Right. Thank you.